Water. Water is one of the abundantly available substances in nature. It is an essential constituent of all animal and vegetable matter and forms about 75% of the matter of the Earth's crust. It is also an important ingredient of animal and plant life. Water is very important for all living beings. Our body consists of 70% of water by weight. Water on the earth is found in 3 states. In the solid form, water is present as ice and snow on high mountains, glaciers, and at the poles. In the liquid form, water is present in the rivers, ponds, lakes, seas, and oceans. In the gaseous forms, water is present as water vapor in the air. Water is a universal solvent. Most of the things, that is, solids, liquids, and gases, are soluble in water. Aquatic plants make food by taking carbon dioxide dissolved in water. Water animals, as well as plants, respire with the help of oxygen dissolved in water. Water interacts differently with different compounds. It overcomes force of attraction between ions and separates them so that they are dissolved. Water has highest specific heat capacity. To put it simply, it takes a very long time to raise the temperature of water. This property is also a boon to aquatic life, as even during hot summers, the temperature of water remains tolerable for them. Dissolution of salts in water. Salts dissolve in water can be best understood by looking at the molecular structure of water. Although the water molecule is made up by sharing of electrons between the hydrogen and oxygen atoms, there is still a polarity in each water molecule. The hydrogen side of each water H2O molecule carries a slight positive electric charge, while the oxygen side carries a slight negative electric charge. This helps water dissociate ionic compounds into their positive and negative ions. The positive part of an ionic compound is attracted to the oxygen side of water, while the negative portion of the compound is attracted to the hydrogen side of the water. For example, consider what happens when salt dissolves in water. Salt is sodium chloride, NaCl. The sodium portion of the compounds carries a positive charge, while the chlorine part carries a negative charge. The two ions are connected by an ionic bond. The hydrogen and oxygen in the water, on the other hand, are connected by covalent, non-ionic bonds. Hydrogen and oxygen atoms from different water molecules are also connected via hydrogen bonds. When salt is mixed with water, the water molecules orient so that the negative charge oxygen anions face the sodium ion, while the positive charge hydrogen cations face the chloride ion. Water, a universal solvent. Water is called the universal solvent because it is capable of dissolving more substances than any other liquid. This is important to every living thing on earth. It means that wherever water goes, either through the air, the ground, or through our bodies, it takes along valuable chemicals, minerals, and nutrients. This has to do with the polarity of each water molecule. It is water's chemical composition and physical attributes that make it such an excellent solvent. Water molecules have a polar arrangement of oxygen and hydrogen atoms. One side hydrogen, has a positive electrical charge, and the other side, oxygen, has a negative charge. This allows the water molecule to become attracted to many other different types of molecules. Water can become so heavily attracted to a different compound, like salt, NaCl, that it can disrupt the attractive forces that hold the sodium and chloride in the salt compound together, and thus dissolves it. Despite its name as the universal solvent, there are many compounds water won't dissolve or won't dissolve well. If the attraction is high between the opposite charge ions in a compound, then the solubility will be low. For example, most of the hydroxide exhibit low solubility in water. Also, non-polar molecules don't dissolve very well in water, including many organic compounds, such as fats and waxes. Thus, water is called the universal solvent because it dissolves the most substances, not because it actually dissolves every single compound. Solutions, suspensions, and colloids. With a few simple observations, you can classify a mixture as a solution, suspension, or colloid. All the three are different forms of mixtures. You are already familiar with solutions and suspensions learned in earlier classes. Solutions. A solution is a homogeneous mixture of two or more components. The dissolving agent is the solvent. The substance, which is dissolved, is the solute. The components of a solution are atoms, ions, or molecules, which makes them 10 to the power minus 9 meter or smaller in diameter. Example: sugar and water. Suspensions. The particles in suspensions are larger than those found in solutions. Components of a suspension can be evenly distributed by a mechanical means, like by shaking the contents, but the components will settle out. Example: oil and water. Colloids. Particles intermediate in size between those found in solutions and suspensions can be mixed such that they remain evenly distributed without settling out. These particles range in size from 10 to the power minus 8 to 10 to the power minus 6 meter in size and are termed colloidal particles or colloids. The mixture they form is called a colloidal dispersion. A colloidal dispersion consists of colloids in a dispersing medium. Example: milk. Activity: how to differentiate a colloid from a suspension or a solution. You can tell suspensions from colloids and solutions because the components of suspensions will eventually separate. Colloids can be distinguished from solutions using the Tyndall effect. A beam of light passing through a true solution, such as air, is not visible. Light passing through a colloidal dispersion, such as smoky or foggy air, will be reflected by the larger particles and the light beam will be visible. Unsaturated, saturated, and supersaturated solutions. You are already aware of the different types of solutions that you have studied in earlier classes. Let us take a quick look at the three types of solutions in this table. Unsaturated solution, saturated solution, supersaturated solution. Made by dissolving little amount of solute in the solvent. Made by dissolving the maximum amount of solute that can be dissolved in the solvent, made by dissolving more solute in a saturated solution by heating the solution. Can dissolve more solute at room temperature. Cannot dissolve more solute at room temperature. Cannot dissolve more solute after heating. Is a dilute solution. Is a concentrated solution. Is a hot and highly concentrated solution. Is used as dilute solutions of reagents in the chemistry labs. It is used as syrups and preservatives at home and in the food industry. It is used mostly to recrystallize fats and sugars at home and in the industry. Suspensions and colloids. You have learned what a colloidal mixture is. Milk is the best available example. Similarly, liquids, solids, and gases all may be mixed to form colloidal dispersions. Depending on the size of the particles of the dispersed phase, colloidal dispersions have been categorized as aerosols, solid or liquid particles in a gas. Examples: smoke is solid in a gas. Fog is a liquid in a gas. Sols, solid particles in a liquid. Example: milk of magnesia is a sol with solid magnesium hydroxide in water. Emulsions, liquid particles in a liquid. Example: mayonnaise spread is oil in water. Gels, liquids in solid. Examples: gelatin is protein in water. Quicksand is sand in water. Water of crystallization. By definition, water that occurs inside crystals is called water of crystallization. Water is often incorporated in the formation of crystals from aqueous solutions. The total weight of water in a substance at a given temperature is also referred as the water of crystallization and is present in a definite ratio. In the given activity, copper sulfate crystals, which seem to be dry, actually contain the water of crystallization. When these crystals are heated, the water present in crystals is evaporated, and the crystals turn into a white salt. The crystalline structure of the salt is also lost. Activity. Take a few blue-colored crystals of hydrated copper sulfate in a dry test tube and heat the test tube. Observe water droplets on the walls of the test tube. The blue color of copper sulfate crystals is lost and the substance has become white. Add 2 to 3 drops of water on the sample of copper sulfate obtained after heating. The blue color of copper sulfate is restored. Hydrated and anhydrous substances. From the above activity, we can infer that the blue-colored copper sulfate crystals contain water of crystallization, and this condition of the crystal is called hydrated. Thus, the blue crystals of copper sulfate is the hydrated form of copper sulfate. When we heat the crystals, the water of crystallization is lost, and the salt becomes anhydrous or without the water of crystallization. Thus, the white-colored copper sulfate is the anhydrous form of copper sulfate. Hygroscopic substances. If you leave the white-colored anhydrous copper sulfate powder for a few days in an open container, you will notice that this slowly turns back into blue crystals. This is because the anhydrous copper sulfate absorbs water, moisture from the air and becomes hydrated once again. All substances that absorb water from the atmosphere and become hydrated are said to be hygroscopic. Even common salt is hygroscopic. It absorbs water from the air and becomes soggy. It loses its dry, crisp feel. Calcium chloride and calcium oxide are other examples. And kept in medicine bottles to absorb moisture because of its hygroscopic property. Important point to remember is that all anhydrous substances may not be highly hygroscopic. Many compounds can exist as both hydrated and anhydrous forms and may not readily absorb atmospheric pressure. Chemical properties. Action of water on metals. Water attacks the metals to a degree varying according to their position in the metal activity series, which is a series of metals arranged in decreasing order of their reactivity. K, Ca, Na attack water. Mg, Al, Zn, Fe attack steam. Pb, Cu, Hg, Ag, Au do not attack water. Sodium, Na, and potassium, K, react vigorously with cold water. Twice Na plus twice H2O gives twice NaOH plus H2. Twice K plus twice H2O gives twice KOH plus H2. Calcium reacts slowly with water, making the solution slightly milky, turbid. Ca plus twice H2O gives CaOH whole twice plus H2. Calcium hydroxide dissolves only slightly in water, making water turbid. Magnesium and zinc react with boiling water, forming their oxides and hydrogen. Mg plus H2O gives MgO plus H2. Zn plus H2O gives ZnO plus H2. Iron does not react with water, but is attacked when steam is passed over red-hot iron. Thrice Fe plus 4H2O gives Fe3O4 plus 4H2. Lead does not react with water. It, however, dissolves in water containing dissolved oxygen. This property of lead is called plumbosolvency. Copper, mercury, silver do not react with water. Action of water on non-metals. On passing steam over red-hot carbon, we get water gas, mixture of CO and H2. C plus H2O gives CO plus H2. Importance of water. In the living body, water is an essential constituent of all living things. More than 70% of our body is composed of water. It is required to transport gases for respiration, food for energy, and waste material. Many of the chemical reactions that regulate life takes place in water. In domestic purposes, it is used in drinking, food preparation, bathing, washing clothes and utensils, and flushing toilets. In agriculture, for irrigating crops and plants. In industries, for industrial purposes in industries such as steel, paper, chemical, and petroleum refining. Hard water and soft water. Water for industrial purposes should be free from those dissolved mineral salts which settle down on the walls of boilers or on the cloth when they are washed before dyeing, etc. Since water can dissolve almost anything in it, therefore, on its journey from hills, villages, etc., water accumulates a lot of dissolved salts. These salts make water hard as they interfere with lather action of soap. The water which lathers easily with soap is called soft water. Some examples of soft water are distilled water and tap water. On the other hand, water that does not lather with soap is called hard water. Some examples are seawater, well water, etc. Hardness in water is caused by dissolved salts of calcium and magnesium. Salts like calcium sulfate, CuSO4, calcium chloride, CaCl2, magnesium sulfate, MgSO4, magnesium chloride, MgCl2, calcium bicarbonate, CaHCO3 whole twice, and magnesium bicarbonate, MgHCO3 whole twice, impart hardness to water. The differences between hard water and soft water are listed in the table. Hard water. Soft water. Hard water does not lather with soap. Soft water lathers readily with soap. Contains dissolved chlorides, sulfates, or bicarbonates of calcium and magnesium in it. Does not contain chlorides, sulfates, or bicarbonates of calcium and magnesium in it. River water and seawater are examples of hard water. Distilled water is an example of soft water. Types of hardness. The hardness of water is of two types. Temporary hardness. Temporary hardness of water is caused by the presence of dissolved salts of calcium and magnesium bicarbonates. It can easily be removed by boiling the hard water. CaHCO3 whole twice on heating gives CaCO3 plus CO2 plus H2O. MgHCO3 whole twice on heating gives MgCO3 plus CO2 plus H2O. Permanent hardness. Permanent hardness is caused by the presence of dissolved chloride and sulfates. It cannot be removed by boiling. Hard water can be softened by adding chemicals such as sodium carbonate, washing soda. Sodium carbonate converts soluble calcium sulfate and magnesium sulfate into insoluble carbonates. These insoluble compounds can be removed by filtration. CaSO4 plus Na2CO3 gives CaCO3 plus Na2SO4. MgSO4 plus Na2CO3 gives MgCO3 plus Na2SO4. Distilling the water removes both types of hardness. Distilled water is the purest form of water. Activity. To remove permanent hardness of water, take some hard water in a beaker and add a small amount of washing soda in it. Stir it with a glass rod. Allow the insoluble substances to settle down as precipitate. Water obtained after filtration or decantation is soft water, but it is unfit for drinking as it contains an excess of washing soda. Thus, permanent hardness of water can be removed by adding sodium carbonate.